Yo, my people, it's your boy Dappa once more. Running with Dappa, day 26. We almost done this thing, people. We're gonna finish up and then see what's next, you know what I mean? But this was about accountability. To be honest, it was all about to challenge myself. Can I do something for 30 days without giving up? I have a new angle today. I don't know if it's gonna work yet. Still testing it out. But essentially, I move the thing on me. I move the treadmill a bit to be closer to my front of my TV. Alright. So we have a art piece. I got that for my birthday, for the 25th birthday. Anyways, here's my fit. My vesty pants. I have a diamond socks. And this shirt for myself, Ugandala shirt, black and red beach shorts. Alright, so we're gonna be running today. And we're gonna be watching, regular tech stuff as I do a lot of the time indoors. And it's gonna be a little bit different. Let me see. And it's gonna be like this. Alright, cool. And yeah, so we have the remote. Gonna speed it up. We're gonna bring it up to about 3.2 miles per hour. Or maybe, 3.8 to the max. You see. And we're gonna listen to some tech stuff as well. So, alright, cool. You all ready for this? Day 26. Going, we got.
So now let's move on to the union find data structure, aka the disjoint sets data structure. And I personally think that this is an underrated data structure. It doesn't really come up super often, but when it does, I kind of enjoy coding it up. Now it's technically a tree data structure, but it's mostly applied to generic graphs, so it can get kind of complicated, but the implementation is surprisingly easy to do with things. Suppose we had a generic graph that looked kind of like this. Maybe we had directed edges, maybe, this is what it looks like. So even though it's a single graph, we actually have two disjoint sets because the entire graph is not connected. We're used to dealing with connected graphs like trees where every node is connected. We don't have usually graphs where we have two separate entities of the graph, but that's the case here. That's the strength of the union find data structure. It can deal with disjoint sets where we can have one or more connected components. This would be considered a connected component of the entire graph because all of these nodes are connected. This would also be a connected component, but the entire graph itself is not connected. So if we were given a graph like this, the strength of the union find data structure would be to count the number of connected components in this case. It can also be used for cycle detection. Suppose we had a graph like this. Union find would be able to determine that this graph does not have any cycles. But if we add an edge like this one, union find would be able to tell us that this graph indeed does have a cycle. Now you might be wondering, can't these operations also be satisfied using just a generic DFS algorithm? And usually that is the case. That's why union find is pretty rare to see. Usually DFS can accomplish find data structure, aka the disjoint sets data structure. And I personally think that this is an underrated data structure. It doesn't really come up super often, but when it does, I kind of enjoy coding it up. Now it's technically a tree data structure, but it's mostly applied to generic graphs, so it can get kind of complicated, but the implementation is surprisingly easier than you would think. Suppose we had a generic graph that looked kind of like this. Maybe it had directed edges, maybe, this is what it looks like. So even though it's a single graph, we actually have two disjoint sets because the entire graph is not connected. We're used to dealing with connected graphs like trees where every node is connected. We don't have usually graphs where we have two separate entities of the graph, but that's the case here. That's the strength of the union find data structure. It can deal with this where we can
Anyways,
have
we're
one
live.
or more connected components. This
Wait, you have a
would be
feeling
considered a connected component.
Keep going.
of
It's not
the
good
entire
deep.
graph.
See, let me
All
go.
of these nodes are connected. This would also be a connected component.
We're waiting for the shoes
entire
and it
graph
look like
itself
it too big
is
for me or something.
not connected.
I feel like it's
So
not
if we were given a graph like this, the strength of the unified data structure would be
Okay.
to count the number of connected components in this case. It can also be used for cycle detection. Suppose we had a graph like this. Union Find would be able to determine that this graph is disjoint sets, where we can have one or more connected components. This would be considered a connected component of the entire graph, because all of these nodes are
4
connected.
people watching.
This would also be a connected
No, it's not
component,
live.
but the entire
4
graph
people going to be
itself
watching.
is not connected. So if we were given a graph like this, the strength of the union find data structure would be to count the number of connected components in this case. It can also be used for cycle detection. Suppose we had a graph like this. Union Find would be able to determine that this graph does not have any cycles. But if we add an edge like this one, Union Find would be able to tell us that this graph indeed does have a cycle. Now you might be wondering, can't these operations also be satisfied using just a generic DFS algorithm? And usually in this case, it can also be used for cycle detection. Suppose we had a graph like this. Union Find would be able to determine that this graph does not have any cycles. But if we add an edge like this one, Union Find would be able to tell us that this graph indeed does have a cycle. Now you might be wondering, can't these operations also be satisfied using just a generic DFS algorithm? And usually that is the case. That's why Union Find is pretty rare to see. Usually DFS can accomplish the same thing in the same time complexity, but sometimes Union Find is more efficient and sometimes Union Find is required. So now let's get into the implementation of the data structure. Suppose we're given a list of edges like these, and we want to determine if this graph has a cycle or not. Let's say we're also given the total number of nodes, which is 4 in this case, so we have 4 nodes here. And these are the edges of that graph. Let's say each edge is directed, so 1, 2 basically means 1 points to 2. Let's say in this case, each edge is undirected, so 1, 2 basically means 1 and 2 point at each other. So how could we use Union Find to solve this problem? Well, first of all, Union Find is a forest of trees. Forest of trees basically means we have a bunch of trees. The way we initialize this, essentially we have a tree for every single disjoint set. Now initially, we assume that all 4 of our nodes are disjoint sets. We don't know any information about these nodes, we just know that we have 4 of them. But now we're going to start going through the edges and connecting these guys together. Now for each node, we don't store a lot of information. We just store what is the parent of that node. Initially, all of these nodes don't have a parent. They're just a single node. But an easier way to do that, especially in terms of code, is just to say that the node itself is its own parent. That's the way I like to implement it at least. But you can see it both ways. Sometimes people will say it doesn't have a parent. I like to say every node is just initialized to its own parent. And at this point, it gets pretty straightforward, actually. We have an edge 1, 2. What do you think we're going to do among these? Well, we had 4 separate graphs. Now we know that 1 and 2 are connected to each other, so we should connect these 2 nodes. So essentially what we do is we take one of the nodes and set it as the parent of the other node. So in this case, I'm going to say 2 is going to be a child of 1. So now 2 has a parent, which is now 1. It was arbitrary how we did this. We could have also taken 1 and added it as a child.
Everywhere we go, everywhere we go.
But it will matter in some cases, but we'll get to that in a bit. We went to the first node, now let's go to the second node. And actually to illustrate things a little bit better, I'm going to do this edge first. So actually let's focus on this edge first. So 2, 4, we want to union 2 and 4 together. So what should we do? Well, we could arbitrarily take one and set it to be the child of the other. We could take this 4 and set it to be a child of 2. Or maybe we could even take 2 and set it to be a child of 4. But 2 already has a parent, so we're running into a problem. We can't arbitrarily pick in this case. The best way to is instead of unioning the two nodes themselves, how about we go from that node all the way up to its parent and then eventually to the root node of, this tree. This is a tree at this point. And we go to the root, which in this case is just one. But, maybe there were multiple chains and there were multiple nodes up ahead. We would keep going until we got to the root. And then we would take the roots of these two trees and then union them together. Now in this case, we sort of have a choice because they're not symmetrical in this case. It's not arbitrary which one we pick. They're not the same size as what I'm getting at. So what do you think would be better? To take this tree and add it as a child of this, which would look something like this? Or should we instead take 4 and add it as a child of 1? Well, this one definitely looks a little bit more balanced, but why is being balanced important? Well, what I just talked about. When we are trying to union two nodes together, in this case 2 and 4, the first thing we want to do for these two nodes is find the parent of these two nodes. Or rather, not the parent, the root of these two nodes. So for 2, the root is 1. For 4, the root is itself. And then after we find the parent, we want to then union these two disjoint sets together so that they form a single disjoint set. But we know we might continuously run the find operation on nodes. So if we have a balanced tree, then the find operation is going to be more efficient than, if we just take this and insert it as a child here. At that point, we have a linked list. That's not really efficient to traverse. Imagine we have to find the root of this child, and we have to go all the way up the chain. Whereas if we take this 4 and, move it to be a child of 1, this is a bit more balanced. We don't have to go up, an entire chain. For 2, we just have to go up 1 step. For 4, we just have to go up 1 step to find its root. This operation that we talked about is called union by rank, which just means height. So we take the height of the trees that we're unioning and take that into consideration. We could do it arbitrarily if we wanted to, but it's more efficient when we union by height. We saw that this tree had a smaller height than this tree, so we took the smaller tree and then added it as a child of the larger tree. And even when we connected them, we connected it straight to the root because that also makes it more efficient to find the root. We could have taken this 4 and connected it over here, but why would we do that? So now we've processed this edge over here. And by the way, based on these two edges, 1 and 2 are connected and 2 and 4 are connected, we would have a graph that looks something like this, wouldn't we? Where 2 is connected to 1 and 2 is connected to 4. But with our union find, we ended up with a tree that looks like this. 2 is connected to 1 and 4 is connected to 1. Well, that's kind of the point. Union find doesn't necessarily accurately represent the graph. It's about being able to detect cycles and about being able to count the number of connected components. So now let's go through the last edge for 1. That means we have to first find the parent of 4, so we would start at 4, go to its parent, and keep going up the chain until we can't go any higher. 1 is the parent of 4. 1 is the root of 4. And for 1, we also got to find the root of it. Of course, it's itself. So now we look for the roots of both of these, and they're the same. What does that mean? Well, that of course means that these two nodes, 1 and 4, are part of the same connected component. That means that we can't union these. They're already a part of the same set. But we could return some value to indicate we were not successfully able to union. We could return false, for example. And the point, union find doesn't necessarily accurately represent the graph. It's about being able to detect cycles and about being able to count the number of connected components. So now let's go through the last edge for 1. That means we have to first find the parent of 4, so we would start at 4, go to its parent, and keep going up the chain until we can't go any higher. 1 is the parent of 4. 1 is the root of 4. And for 1, we also got to find the root of it. Of course, it's itself. So now we look for the roots of both of these, and they're the same. What does that mean? Well, that of course means that these two nodes, 1 and 4, are part of the same connected component. That means that we can't union these. They're already a part of the same set. But we could return return some value to indicate we were not successfully able to union. We could return false, for example. Basically, that would indicate that these are already connected. And in the context of this problem, that would indicate that this graph has a cycle because we're connecting two nodes that were already connected. That's at least assuming that all edges here were unique. In this case, they were unique. That means we must have a cycle. Let's draw what this graph would look like to confirm. We have a 1, we have a 2, and we have a 4. 1 and 2 are connected, 4 and 1 are connected, and 2 and 4 are also connected. I mean, we do also have a 3, but it's not connected to anybody. So this is our graph, and our graph indeed does have a cycle. At least one of the components has a cycle. So now let's move on to the code. It's surprisingly not super difficult, but there are some gotchas, and there are a couple things that we didn't talk about in the drawing just yet. So we have our union time class. The constructor would usually take one parameter, usually telling us the size of our set, n in this case would be the number of nodes of our graph. And we know that for every single node, we want to keep track of what its parent is. And I think the easiest way to do that is with a hash map. You can also do it with an array, especially if you're given some values, in between a range of 1 through 4, for example, that could be handled with an array. But I like to do it with a hash map. It's more generic. It works pretty much the exact same anyway. Now, for every single tree, we also want to keep track of its rank. And by rank, we mean height, because we want the height of our trees to be as small as possible. That makes our find operation more efficient. Now, when we have a tree like this, every one of these has a rank. So the height, aka the rank of this guy is 1, the rank of this guy is 1, the rank of this guy is 2. But of course the ranks of these don't really matter anymore. They're irrelevant at this point because we're never going to be unioning these guys anymore. Anytime we want to union 2 with somebody else, like for example 3, we're going to end up going from 2 up to its parent. That's where the find operation comes in. Given some node, we want to find its parent. We want to do that so that we can perform the union operation. How do we find the parent? And by parent, we usually mean the root parent. So P in this case is going to be the parent of N. And by the way, we initialize the parent as itself in the constructor, and we initialize the rank of everybody to 0. That's sort of a default value. We could also have done 1, it depends. Do you count the height of a single node to be 0 or 1? It doesn't really matter as long as you're consistent, because it's all about comparing the height of one node to another. The height of this would be 1, the height of this would be 0, so of course this one would have a larger height. So to find the root parent of 4, we would go to its parent first of all, so we'd have a pointer to its parent. We could do that using our hash map of parents. And then we would essentially keep traversing up while P is not equal to its parent. So we know that's how we're kind of setting it. We're initializing every node to have its own parent. So that's how we know we can stop going. Up the tree. So we'd start at 4, we'd go to 1, we'd see that 1 is its own parent, so we can't really go any higher. At that point, we would stop. We would return P at that point. Now, this one line of code might be a little bit confusing. Basically, what we're doing here is path compression. It's an optimization that I didn't talk about yet, but suppose we had another node down here, like 5. It's pointing at 4. Let's say we run the find function on 5. We go to 5, we go to 4, then we go to 1. This is its root parent, and then we would return that. Now, simultaneously, as we're going up the chain, we can also shorten it. We can also shorten this chain, and it won't affect the time complexity complexity of our find function. So why shouldn't we do it? It's an optimization that will help us if we ever run find on 5 ever again. 5's parent is 4, but what we're essentially saying is we're going to set the parent of 5, instead of being 4, we're going to set it to its grandparent, because that will shorten the chain. So essentially we remove this and now have a direct link from 5 to its grandparent. And we keep doing that as we traverse the chain. This doesn't make the find operation more efficient as we do it the first time, but if we ever run find on 5 again, it will be more efficient. And since it's just one line of code, it's a good thing to do, but it's not always required in using find. Now finally, we can move on to the union function. Given 2 nodes in this case, n1 and 2, for example 2 and 4, we want to union them together to form a single set. So what we should do is find the root parent of n1 and the root parent of n2 and then union them together. But in this case, both of them have the same root parent. So if that were the case, we wouldn't do anything. There's nothing to perform. We can't perform a union, so we should return false. False is to indicate that the union was not successful, that these are already a part of the same set. If that wasn't the case, for example, we're trying to union 4 and 3.
Kevs, can you do me a favor? Can you come here? Can you do me a favor? Before you, oh shit. Yeah. Hey people, before I drop my soul up here.
Where they? Oh goodness, no.
I'll put it on there. Oh. It's not gonna work like that.
Okay, what's gonna put it so something there?
Yes, go on.
Okay.
Yeah.
Turn it.
Whew, Kels, I'm so tired. 25. No, let's put it this way. On top of it. Put it in front of the the goal. Yes?
Huh?
Put it in front of the goalie. Okay, sure.
Oh.
Thanks. Sure, this not a good job. Firm. Turn this camera.
Oh.
Together, we would of course get the root parents 1 and 3 as its own parent, and then we would union them together. Now the most easy thing we could do is just get rid of all this code, all this, and just have a single line of code like this one where we arbitrarily pick, for one of these nodes, we want the other one to be its parent. So, maybe we say 1 is going to be the parent of 3. So maybe we'd say that this tree is going to be the child of 3. Then we get rid of this and we get something that looks like this. That's if we did it arbitrarily, and that wouldn't always be efficient. So what we try to do is union by rank, aka union by height. Which one of these guys has a smaller height? Well, the height of this is, let's say, 0, and the height of this is 1. So this one has a smaller height. Therefore, this one should be a child of this guy. And that's what these if statements are doing. It's saying if the rank, aka the height of P1 is larger, then P1 should be the parent of P2. If P2 is larger, then P2 should be the parent of P1. So in this case, we would set 3 to be a child of 1. Now, if those are the case, basically if the heights are unequal, in this case, this had a larger height than the other one, doing a union operation is not going to affect the height, because if this one had a smaller height anyway, and we're directly adding it to the root, the height of this is not going to change. It's still 1, as you can see. But if we ever did an operation where we had unequal heights, but if we ever did an operation where we had equal heights, for example, let's say these two were not childs of 1, both of these have a height of 0, let's say, and that's going to be the else case where the heights are equal. Then we would arbitrarily pick, let's say this one is going to be the parent of 3, so we'd take 3 and add it to be a child of 1. At that point, we would have to increase the height. But we only have to increase the height by 1 because both of these heights were equal. They were 0 in this case, but I'm going to use a value like n because it's a variable. The height of this tree was n, the height of this tree was also n. But now this tree is a child of this guy, so we added a bit of distance. We added this much distance. We added an edge of 1. So now the new height of this is going to be n plus 1, right? That makes up for this distance, and then, this tree has a height of n, which in this case is 0, but it could have been bigger. But that's the main idea. Now, the important thing to know about union find is, of course, the time complexity. Union is a pretty straightforward operation, actually. Like this combination, because we already have the parents at this point, we're essentially just connecting, two nodes together. That is a constant time operation. What's not constant, though, is what we have to do before. We have to find the root parents of two nodes. So the bottleneck is coming from the find function. Now, in the naive case where we don't implement path compression at all, and we don't implement union by rank, then the find function would be linear time, because we might end up with trees that are just connected as if they were a linked list. That would not be very efficient. Those are imbalanced trees, and then traversing up them would be a linear time operation. Now we can cut this to log n by just doing one of the two operations. We can either implement path compression, which is just a single line of code. That will take our find function, at least on average, and change it from being an n time function to being log n. Or we can decide to implement union by rank, which does take some more code, but I don't think it's a super complicated thing to achieve, which will also get our time complexity to be log n for find, because it will result in more balanced trees. The height of the trees will be smaller. But if we implement both path compression and union find, we get a pretty complicated math function, which is written like this, and it's called the inverse Ackermann function. You won't really have to memorize this. I don't think it's super important, but in case where we don't implement path compression at all, and we don't implement union by rank, then the find function would be linear time, because we might end up with trees that are just connected as if they were a linked list. That would not be very efficient. Those are imbalanced trees, and then traversing up them would be a linear time operation. Now we can cut this to log n by just doing one of the two operations. We can either implement path compression, which is just a single line of code. That will take our find function, at least on average, and change it from being an n time function to being log n. Or we can decide to implement union by rank, which does take some more code, but I don't think it's a super complicated thing to achieve, which will also get our time complexity to be log n for find, because it will result in more balanced trees. The height of the trees will be smaller. But if we implement both path compression and union find, we get a pretty complicated math function, which is written like this, and it's called the inverse Ackermann function. You won't really have to memorize this. I don't think it's super important, but what I'm trying to get at is if we implement path compression and find by rank, this is a function, but it essentially reduces to constant time. Even for really large n values, it will usually be a constant time operation. Not literally, but it can be simplified to that in most cases. But this find function is usually not going to be run a single time. It's going to be run a bunch of times, as we were doing right now. We're trying to connect graphs together. In our example, this would be run for the number of edges that we have. Let's say that is denoted by m. So, in general, the time complexity of union find, if we have this many edges, let's say, would be big O of m times log n. But we saw if we implement path compression and union by rank, this log n can be, essentially reduced to a one-time operation. So in that case, our union find would be the time complexity of the number of edges that we had. That's why in some cases, union find can be more efficient than a DFS or cycle detection or counting the number of connected components. This can definitely be a complicated data structure for beginners, but I hope that this walkthrough did make things a bit more simple for you. So next, let's learn about segment trees. And to be honest, this is definitely the most complicated tree structure that we've looked at so far. So before we actually dive into what this is, let's try to first understand the motivation behind it and what kind of problem it can solve for us. Suppose we were given an array of values, so a range of values in this case. And on this array of values, we want to support two main operations. We want to be able to update a value at some index with a new value. That's a very simple thing to do. You can easily implement this with an array. You can just, overwrite the value at that index. That's a very efficient thing. We could solve that in constant time. Now, when it comes to querying some range, so between some left and right index inclusive. So let's say this is the left index, this is the right index. We want to get the sum of that range. That could be one possible query, getting the sum of that range. And that's what I'm going to stick with for this example, because that's really the most simple thing that we could possibly do. This is kind of the textbook problem behind segment trees, so that's what we're going to be focusing on. Now, in the worst case, we could just iterate from left to right and take the sum of all those values. That could be accomplished in O of n time in the worst case. There are some optimizations we could do, like taking a bunch of prefix sums to get this query to actually be a constant time operation in general for this example, because that's really the most simple thing that we could possibly do. This is kind of the textbook problem behind
this guy explains things so nice.
Now, in the worst case, we could just iterate from left to right and take the sum of all those values. That could be accomplished in O of n time in the worst case. There are some optimizations we could do, like taking a bunch of prefix sums to get this query to actually be a constant time operation in general, but that's assuming that we can't update the values. Once you add this in, making it possible that we could update values in the array, then there's no way to get this query range to be constant time. It would be O of n time with an array. But with a segment tree, actually, we can solve these problems in log n time each. So we can update in log n time and we can query in log n time. Now, the update is actually a downside because previously with an array, we could do that in constant time. So we're adding a bit more overhead to the update, but the trade-off is that our query is going to be much more efficient. So assuming that we're always updating and always querying our data structure, we're doing that a lot, we're going to have a bunch of log n operations, whereas with an array, we'd have a bunch of, constant time operations, but the downside would be we'd have a bunch of linear time operations, and we know these are way more expensive than log n, so it's better to have log n. So that's what this is about. So that's kind of why this is called a segment tree as well. It takes segments, it takes an array and breaks it up into segments. So the general structure is that for the entire array, the root node would represent the range for the entire array. But as we go down to children, we take this array and we break it up. So the left half of the array would belong to the left node, and the right half of the array would belong to this node, and then its children would actually break it up as well, so they would get smaller and smaller portions of the node. So they would get smaller and smaller portions of the array. Now the overhead of this is that when we update, we can't just update a single value, because suppose we're trying to update this value over here. We would have to update the root node because it, has that value. We'd also have to update the right child because it has that value as well. And we'd have to sort of update an entire chain of the tree. So that's where the log n idea comes from for update. We'll talk more about the query range in a bit, but for now, let's focus on the structure of a segment tree, how we can build one, and then how we can actually implement these functions in log n time. So suppose we were given an array that looks like this, indexes 0 through 5. The values aren't super important, but they will be relevant when we're calculating the query range sum. But given this, how would we represent it with a segment tree? Well, like I said, the root node is supposed to represent the entire array. So what we would say is the root node represents indices from 0 through 5. And then we take that input and essentially divide and conquer it. It's a bit similar to merge sort, actually, when we have an array and we want to break it up into equal halves until we can't do so anymore. It's the same idea here, actually. We want to take this and break it into two halves. So what we do is take the left and right indices, add them together, and divide by 2. That gives us our mid value. So in this case, it would be 0 plus 5 divided by 2, rounding down. So in this case, our middle value is going to be 2. So what we do is we take the left index from here and the middle index that we just calculated, and these are going to be the boundaries of the left child. The right child is going to be bounded by m plus 1 and the right boundary of its parent. So m plus 1 and right. Now this is the formula. The actual values themselves in this case are going to be 0, 2 and 3, 5. And at this point, we would recursively do the same thing for the left and right child. So we're going to continue to do this. So for this node, we break it up into 2 equal halves. In this case, when we calculate the midpoint, it would be 1. So the left child is going to represent the range from 0 to 1. The right child is going to represent the range from 2 to 2. So notice how this range is of length 1. It's from index 2 ending at index 2 as well. So it can't be broken up anymore. So it's not going to have any children. And for this node, it can be broken up one more time. The left child would be from 0 to 0. The right child would be from 1 to 1. And quickly, let's do the same on this side. Left child would be from 3 to 4, and right child would be from 5 to 5. We found another base case, and this one can be split one more time to 3, 3, and 4, 4. Now, each of these nodes is supposed to represent a range, but why do we care about that range in the first place? Well, in our example, we care about the sum of every single range. So as we build this tree, there was one last thing I didn't show you. When we actually reach a base case like this one, there's a third value we would have. Right now, we have the left and right index of that range, but we also want the sum of that range. So it's from 0 to 0, so that's a base case. The sum is just 5. So I'm going to put that 5 next to it. For 1, it's going to be the same thing. We just take the value at 1. Another base case over here is 7. 3 and 4 have values 1 and 4 at them. And lastly, index 5 has the value 2. And as we would have computed the base cases here, and then we recursively pop back up, we would also want to have the range sum for all of these nodes as well. Now, for this one, we wouldn't have to manually calculate it. We would just get it from its left and right child and then add those values together. So 5 plus 3 is 8. So I'm going to put an 8 next to this guy. And this parent would do the same. 8 plus 7 is 15. For this one, it would be 1 plus 4. For this one, it would be 5 plus 2. And for the root, it's going to be the sum of the entire array. And luckily, we don't have to go through the entire array to calculate that. That's the whole point of this segment tree. We just have to look at this guy and this guy, add them together, we get 22. Now, before we go any further, let's take a look at the code for implementing what I just talked about. So suppose we had a segment tree class. Our constructor in this case could possibly take some total value, for a node. As we construct a node, what's that total value, which I, drawn in green. In this case, left and right refer to the left and right children. So these are going to be pointers typically. It's going to be a bit confusing because we also have two variables called L and R. I use these to indicate the indexes. Of course, I could have used a more descriptive variable, but then the rest of the code would also be a lot larger, because you can see we're using these left and right indices a lot. And left and right, of course, refers to the left and right boundaries of a node. What range does that node represent? In this case, this node represents the range from 0 to 5. Now, this is a static method for actually building a segment tree. We could have, of course, implemented our constructor using this method instead of, taking in a total left and right value. We could have just taken in an array of numbers and then constructed our segment tree, within the function. But this is the approach that I'm taking. The time complexity is linear. So build is going to be a recursive algorithm given some array and given some left and right boundaries similar to merge sort. We want to break that array up into, smaller arrays by half and then create nodes for each portion. If we, of course, get to the base case, which, any of these leaf nodes represent, where we just have a range of 1. So basically, if left and right are equal, we create a segment tree node. The total value that we pass in is just the value in the array nums at that position. And the left and right boundaries, of course, are just going to be those left and right boundaries. And at that point, we would return. That's the base case. Now, if we don't have a base case, for example, the root, then we calculate the midway point, just like I talked about, left and right divided by 2. And we create a temporary root node for this. We don't know its total value just yet, right? We don't know the total value, but we do know its left and right ranges. So for the total value, we initially put 0, but for the left and right ranges, we put 0 and 5. It's just like how I talked about, we have to go to the bottom and calculate the total value for the leaf nodes, and then we work our way up, calculating it for this node, and then calculating it for this node, and then calculating it for this node. We do it bottom up, similar to merge sort. So with that temporary root node, then we go ahead and build the left side of the heap and assign it to root.left. And then we build the left side of the segment tree recursively and assign it to root.left. The variables we pass in, the input array nums, and the indices, just like how I talked about, left and middle. When we build the right segment tree, we pass in middle plus 1 and the right index. After we've calculated the left and right children, then we can calculate the sum of the root node by taking the left and right sums. So it's actually not super difficult. It's probably not a data structure you would come up by yourself, but once you know it, it's definitely manageable. Another observation about this tree is that it's sort of like a heap, actually. Heaps are full binary trees. It means that every level in the tree is going to be full except possibly the last level. But this is not quite a full tree in this case, because another property of heaps and full trees is that if the last level is incomplete, the nodes will be filled from left to right. But here you can see that we would have two nodes that are children of this node, but we don't. We have a gap over here, and then we have two more nodes over here. So segment trees actually commonly are implemented using arrays, just like heaps are, but since we have gaps, it's harder to implement them with arrays compared to heaps. So I generally prefer to implement them with nodes, like I'm doing right now, nodes and pointers and all that. But you definitely can do them with arrays, similar to how we implemented heaps. So now let's talk about how we would update a value. And like I said, it's going to be a log n time operation, not a constant time operation like with an array, but we are still given an index and a value. So let's say we're given an index value of 3, and the new value is going to be 4 now. How would we do it? With an array, it's really easy. We go to index 3. But with this tree, it's going to be harder. By looking at the picture, we know we want to go to this node because, of course, it's the one that represents index 3. We know with our segment tree, every leaf node represents a single index. This leaf node, these, and this one. So, of course, we want to go to that leaf node. How do we find it, though? How do we search for it? It's similar to how we built the tree in the first place. We know that the root node represents the range from 0 to 5. So where would index 3 be? Would it be on the left side or would it be on the right side? Well, we can answer the question the same way that we actually built these two sides, by taking 0 plus 5, adding them together, calculating the middle. The middle in this case is going to be 2. And we know that the middle value itself always went on the left side, right? We said that the left node is going to be L to index M. So if we're looking for index 3, clearly 3 is greater than the middle value, so it must be on the right side. That's essentially this line of code over here. If we're calculating the middle index, and if index is greater than middle, then we're going to go to the right side. But if it's not the case, then we know that the index is less than or equal to middle, and then we would go to the left child. And as with most trees, the best way to do this is recursively. So that's what we do. On the right child, that's what self.right is in this case, we call the member function update, the recursive function update, which belongs to the segment tree class, which belongs to the segment tree object. We pass in the exact same parameters. We're still looking for index 3, and we want to update the value to be 4. So now we're at this node. We do the exact same thing. 3 plus 5 divided by 2 is going to give us index 4. Our index greater than 4? Nope. So then we're going to execute the else case. We're going to go left this time. We're going to be over here. 3 plus 4 divided by 2 is going to give us 3. So is 3 greater than 3? Nope. Then we're going to execute the else case. So now we're going to be over here. We finally got into the base case. Our left and right indices are equal. So we got to a leaf node. If we get to a leaf node, that must mean we got to our destination. We're assuming here that the update is always going to be called for a valid index. If it's out of bounds, then of course this is not going to work. But now that we're at the base case, what are we going to do? Well, this value 1 over here, let's overwrite it with the value 4. So that's all nice and dandy. And at this point, you might think we're done. But remember what this segment tree is supposed to represent. Every node is supposed to represent a range of values and the sum of that range of values. Since we updated one value, we at this point have to update every value in the chain of that value, but essentially all the ancestors of that value, because they're the ones that are affected. The sum of this guy is not going to change. None of its descendants were updated, but this one had its child updated, so it has to be updated as well. The good thing is, since we were doing this recursively, it's going to be very easy, because as we pop back up to every one of the parents, we can just update the sum of that one. So after our base case updates, we're going to return. We know we're returning from one of these if-else conditions. We don't even care which one though. All we know is that for this node over here, one of its children were changed. We might not even know which one. We don't know, was it the left one or the right one? Who cares? All we know is we just have to take the sum of both of the children, add them together. That's a constant time operation, so who cares? We just add them together, and then we can update the sum of this node. So to update 5, we can just take its children, 4 plus 4, and add them together, and then we get the new value, 8. And as we pop back up to the parent again, we're going to do the same thing. Get rid of the 7, add 8 and 2, we get a 10. And now we go back up to the parent, get rid of this 22, add its children together, 15 plus 10, that's going to give us 25. So now we've updated our segment tree. You can see why it runs in log n time, because we're just going down one path and then of course going back up that path. But that is essentially the height of the tree. We know the tree is going to be balanced because that's the whole idea behind merge sort. We're breaking it up into equal halves every single time. So this tree is always going to be balanced. Therefore, the time complexity is always going to be log n, where n is the size of the range, which represents roughly the number of nodes as well. Now, finally, the reason we implemented this data structure in the first place to calculate a range query, in this case, the range sum, of course, over this range of values from index left to index right inclusive. Let's start with some basic queries. Let's say the input we're given is from 0 to 5. We would start at the root node, and we would see that this node actually exactly matches that query. And then we would return the sum associated with it, which is 22. So that's the best case, of course. We're taking the sum of the entire range. So obviously that would be a constant time operation. Now let's say we did kind of the opposite, where the left index is 5 and the right index is 5. Then, of course, we don't execute the base case immediately, but we're going to do the same thing we sort of did before. We're searching for index 5 at this point. How are we going to find it? Well, we're going to take 0 plus 5, add them together, divide by 2. We're going to get a mid value. In this case, that mid is going to be 2. And remember, this mid value was used when we created the left node. The left node went from index left to mid plus 1. And the right node went from mid plus 1 to index right, where right is this node and left is, this 0. But the more complicated thing this time is that we're not searching for a single index like we were when we were doing the update. In this case, we're actually searching for a range of indices, which is still possible with a segment tree though. That's the whole idea behind it, but it's going to be a little bit more complicated. The idea is that this node represents a range, and that range is broken up into 2 ranges like these. We're searching for our own range. Where does that range lie? There are 3 possibilities. From this node, the entire range lies in the right subtree, or the entire range lies in the left subtree, or maybe the range overlaps with both the left and right subtrees. Let's start with the simple case, which is that the entire range lies in the right subtree, which is the case here. But how do we know that? Well, when we're given a range left and right, we know that the left value is going to be less than or equal to the right value. So if we know that the left value that we're searching for, which is the smallest value that we're searching for, is greater than the mid value, and sorry, I just realized I had mid plus 1 over here. That's a mistake. This should have been just mid, from left to mid, and this one is mid plus 1. Really sorry about that confusion. Hopefully you caught it earlier. But 5 over here is greater than the mid value. That means the smallest value that we're looking for is greater than the mid value. Therefore, the entire range must be in the right subtree over here. So there's no need to go to the left subtree at all. So, in terms of code, that's the left range that we're searching for is greater than the middle value of the current node that we're at. The code can be a little bit confusing to read because we have a bunch of different variables. We have the nodes left and right values, which are, these left and right, and we have the left and right indices that we're searching for. And by the way, the opposite case, instead of 5, 5, maybe we're searching for 1, 1. In that case, we would see that even the largest value that we're searching for, our right index, which is 1, is less than or equal to the mid value, which in this case we calculated the mid to be 2, if even the largest value is smaller than mid, then that must mean that the range that we're searching for is somewhere here on the left side. Another way to visualize this idea is sort of with a number line, because that's essentially what ranges are in the first place, right? We have a 0, which is for this node. We have a 1, we have a 2, we have a 3, we have a 4, and we have a 5. If we're searching for the range that's just 5 to 5, of course from here, we're gonna go search in the right subtree. If we're searching for the range that's 1, 1, of course from here, we're gonna go to the left subtree. But if we were searching for a range like 2 to 4, like this, then of course we would have to go to the right and the left subtree. That's kind of what I'm getting at here, because all these nodes simply represent a range. So that's the idea. Now let's actually walk through this example 5, 5. So we know we're going to go to the right child first, and at this point we're going to do the same kind of computation. We're going to calculate the midway point, which is going to be 4. The left value is greater than 4, so again we would go right here, and this would be the base case where we execute this and we simply return the sum, which is 2, and then we pop that 2 back up and up and up, and then that's the result we would return for this range query. And I could show you the same example when we're getting the range for 1, 1. It would be the exact same. We would just keep going down until we get to this node. But the more interesting case is going to be a range like 2, 4. What's the range sum of this? So we would start at the root, we would calculate the midway point here. We know, of course, it's 2. And in this case, neither the first if statement or the second one would execute, because our range 2 to 4 is on both sides of the tree. We have a 2 here, we have the 3 and 4 over here. So we have to go to both sides to calculate the total that we're looking for. So the else case does exactly that. We call the range query function recursively on the left child and the right child. For the left child, we simply pass in the range from left to mid, and on the right side, we pass from mid plus 1 to the right. So we called 2, 4 on the root node. Now on the left node, what we would call is 2, 2. Recursively, we'd want to calculate the range sum query of 2, 2 from the left subtree, and also calculate the range sum query on the right side from 3 to 4. And once we solve both of these subproblems, we'll pop back up to the root, add those values together, and then that's what we're going to return. So before we do that, we actually have to calculate it. So from this side, we would end up executing, we would calculate the midway point here, it'd be 1. We'd see that the left value here is even greater than the middle. So we know that the range is going to be on the right side over here. And that's exactly where it is. We have a 7 here. So from here, we'd pop that 7 back up to the parent, and then that 7 would be popped up to the root. Now from the right side, we're going to do something similar. We're going to calculate the mid of this, 3 plus 5, which is 4. Even our largest value in the range is less than or equal to 4. So we know that this range can be calculated exclusively from the left side. So then we go to the left side, and you might think, well, we have to go to the base cases and add those together. But this is the beauty of the segment tree. We don't even have to go to those leaf nodes. We have exactly what we're looking for over here. And this is not uncommon for segment trees. It's expected that we usually reach our answer before even getting to leaf nodes. So we're trying to calculate the sum from 3 to 4. We have that already. It's 5. So we take that 5 and we pop it back up to the parent. So the solution that we're looking for is 7 plus 5, which is 12. So that's what we would return from our recursive range sum query. And just to verify, you can see that the value 2 had 7, 3 had 1, 4 had 4. So add those together, it's also 12. So that kind of verifies what we're trying to do here. Now, the only thing you might be wondering is, why is the range sum query log n? I mean, these steps make sense. Usually we're going to go down one branch, but this else case makes things more complicated. If we have to go down 2 branches, that's not too bad. But if we have to, from here go down 2 branches again, and from here go down 2 branches again, and we have to keep doing that, it surely can't be log n. We might have to end up traversing the whole tree, wouldn't we? Wouldn't that be a linear time algorithm? Well, first of all, the answer is no. it's safe to assume that the range sum query runs in log n time. And the reason is that at any level of our tree, we would look at most a constant number of nodes. For every level, we would look at most 4 nodes. I believe that's the number. So in reality, the worst case time complexity would be 4 times log n. So that of course reduces to log n. So when it comes to standard algorithms like this, even in coding interviews, you shouldn't be asked to prove the time complexity. That would be a problem in and of itself. And for this problem, it's definitely not trivial to prove the time complexity of this. But it's safe to assume that it is an efficient algorithm. So if this was your first introduction to this segment, please, I hope this made sense. It's definitely not.
Hope you guys listened and learned. As usual, you can go check it out on the website. I'm here as NeetCode.io, and I'm here running while learning concepts. After the concepts, I go and try to code up as much as I can using a technique called spaced repetition. So I watch something, and I go back and I watch just one video, and then try to do some questions from it. And that way, it keeps my mind fresh. Anyways, y'all, it's a pleasure. 15 seconds left. And you know, we started, we walked for some, we ran for some. But at the end of the day, we kept moving. Alright? So keep it simple, sunshine. Amazing! Whew. Remember what I said. Keep yourself accountable. I just started. 5 minutes is a good start. And then little do you know it, 5 become 10, 10 become 20, and yada yada. Amazing.